Okay, more questions to Yun? If no, please join me in thanking the speaker once again. And the next presenter is David Grotner. He's doing some like urgent work, but in spite of this, he volunteered to substitute Boston, who is cannot come today. And the presentation by David is a logical continuation of the presentation by Yun. So in the presentation by Yun, one assumes that spin is a good quantum number, and there are so many spins up, there are so many spins down, and their number doesn't change in time. But there are realistic situations when in the system spins are flipped. And for such situations, spin polarized calculations are insufficient, and one needs to do so-called SOC or SOI, spin orbit interaction added to the coupling. So David, floor is yours.
Okay. So, switching slides. There we go. So, much like Yulin, a lot of this has been gone over earlier, but we need the input overlap files, the position files from the molecular dynamics, and then we need several different scripts and in-car files. So the major difference with this one is that we need two in-car files compared to the spin restricted or spin polarized. So as we go, and this is just a list of where you can find them. They're primarily in the bin, either directly in the bin or in the in-car or spinner folder in the bin. So when we look at the Cori submission file as mentioned, we have the B script as our what it's running, and then we note that we can determine the amount of nodes and runtime and name and etc. But the amount of nodes is important because unlike our normal jobs where we can determine the number of cores directly in this file, we need to show the number of cores in our B script file.
David, can you show previous slide? What is VASP NCL? As I remember, when
so that's
yes, go ahead.
I was going to mention that on the next slide, but so that wasn't right. So that's the, why can't I think of the right term right now? Executable. That's not the right term. So that's the mode we need to run it in for our non-collinear and spin orbit jobs.
So why in all previous speakers, and typically we were practicing VASP underscore STD standard or VASP underscore GMAM for gamma.
Yeah.
So why you select not to use previous ones and use this VASP NCL? Is it a critical point? What is it?
Yes, that is a critical point for this. But if we go to this slide, so this slide, you'll notice that the major difference with this method is we're actually running for each coupling. We're running it twice. We're running one with a gamma or a standard point, and that's generating a charge car file primarily for us. And then we're running the NCL executable, and that's where we're getting our wave car file from. Lost track of my thought that I was saying. So yeah, the NCL is critical for this method. So if we look, we have our spin polarized calculation, and I'm just using gamma here to run it. That's generating a charge car file, which makes our non-collinear job run smoother.
Okay, Aaron, would you like to add a very basic, very general comment of what is the nature of VASP-NCL? What is the difference in orbitals representation compared to what we saw before? And I'm sure David can answer it, but Aaron needs practice before his defense.
Well, I guess the last presentation, Yulin talked about spin polarized. So that means your orbitals have either spin up or spin down, and then they're fixed to like one direction. So along the z-axis is the direction. But then with non-collinear, you can create orbitals which can have projections in x, y, and z. So it's superpositions of spin up and spin down.
Okay, so one orbital may contain any projection of a spin.
Yes, so it could be half spin up, half spin down, or any combination in between.
And if one wants to read more about it, one should look for which keyword in Wikipedia.
Bloch sphere.
And for orbitals that include both
spinners.
Yeah, spinners. SPINOR. So this VASP-NCL allows specific format of orbitals for any orientation of spin, and this format of orbitals is named spinners. Yeah, thank you, Aaron. Thank you, David. David, please continue.
So in this, we're noting our number of cores in the bscript file instead of in the Cori file. So it's important that you know how many nodes you select here so you can put the correct number of cores in the bscript file. And much like Amir was talking about, you can select your postcard file. So in this one, I am starting with step 145, and I'm then continuing up to step 200. So yeah, the major difference is that we're doing these two steps. So what I have outlined in blue here, and I have it slightly, I have it not doing it in this specific one because of how I was continuing, but I have outlined in blue the code that saves all the output files that we're interested in. So they'll save all the oscillator strengths, the out cars, the OSI cars, the couplings.
David, I have a quick question, which sorry to interrupt. Maybe you were planning to address it anyway. So in the previous presentation by Yulun, which was very intense and short, and maybe some of that in this missed but there were two sets of couplings, one for spin up, one for spin down. Yeah. Those of us who were practicing absorption of transition metals, for example, Sarah and Lola and some other of us, remember that there are, for transition metals, one needs to have oscillator strengths for spin up and spin down.
Yep.
But here in your spinner representation, do you need to have separate sets of data for energies and oscillator strengths and couplings up and down, or there is some merger of format? Can you please comment on this?
No, you don't. We don't have them separated. It's they're like Aaron was explaining that the spin can be whatever direction it wants. So they're all. It's like a merger, like you were talking.
So by the format of output, it will be the same as spinless.
Yes, it will be the same as spinless, except every band has one electron instead of two.
Mm-hmm. Excellent. Sorry for interrupting, and please continue.
So, and then this line just marks where it goes from our initial setup to the loop setup. So after this yellow line is where it starts creating a loop for the XXX files. So much like someone showed today, this is what your directory is going to look like at the end. And you notice that I've just zoomed in on a section of this so you can see it easier. You notice that everything has coupling dot XXXX, and I set mine up so it gives a 4-digit because of the MATLAB code I'm using. But depending on what script you're using, you may only be a 3-digit. But so you notice that there's all sorts of coupling files and oscillator strength files. And one thing to note, I didn't mention it when we were looking at it earlier. All the oscillator strengths have a VC, CC, and VV. That's indicating the band that we're comparing with. So valence versus conduction. So when you do this method, you're going to get 3 oscillator strengths for each run that you do.
Oh, so it will be occupied and unoccupied.
You'll get an occupied, an unoccupied, and interband.
So VC will be from occupied to unoccupied as our regular oscillator strength.
Yes.
And other two, VV and CC, will be valence to valence, conduction to conduction, occupied to occupied. Okay, yeah, thank you.
Yes. And then finally, the coupling file. And once again, this is a square matrix. So if you look at the top, you can see that the 0, 0, 0 in the first corner, and about 2/3 of the way down, you see where the second line starts with the 0, 0, 0 in the second position. And that's the end of my PowerPoint.
Okay, please join me in thanking David. It is a very important skill set, and since slides are shared, I think some of us will use it, and Boston, who will likely watch it in the recordings, will practice it for his project. So, any questions to David, either typed in the chat line or verbal?
May I repeat your question?
Yes, please.
Dr. Karen, so where should we use this SOC coupling calculations? Where is it the case?
Yeah, David, please try.
So this is important for heavy models that include heavy atoms.
Any additional mechanical explanation why heavy atoms need this spin orbit? I have no doubts you know the answer. Maybe Aaron has already ready words to formulate. Aaron, would you please try to tell why heavy atoms need spin orbit?
So heavy atoms that are like in the bottom right area of the periodic table, they're like E and D electrons have heavy angular momentum, so they're spinning very, very fast. And the speed at which they're rotating can interact with the spin.
So electrons that move, thank you, Aaron, with very high velocity or having large angular momentum create magnetic field, because moving charge creates magnetic field, and this magnetic field may act on the spin of electron itself and induce flipping of a spin. So if we speak about, let's say, hydrogen atom, which has only s orbitals where there is no rotational motion, this effect is completely disabled. But as soon as we have p, d, f orbitals, especially in the heavy elements, this effect becomes more and more important. So it is one aspect. Another one, so one of the potential client of this method is Lola, if she decides eventually to do this kind of calculations. So if one is looking for emission of models with transition metals, there are channels of emission with conservation of spins, which happen quick and are called fluorescence. And there are channels of emission when spin multiplicity is changing from excited to ground, for example, from triplet to singlet. So photo emission with a change of spin multiplicity. And the calculations with the spin orbit coupling are critically needed to catch this mechanism of emission. If all your atoms are carbons and hydrogens, and number of electrons is paired, then there are chances that you do not need this effect and this code. If you have transition metals, magnetic materials, then from your knowledge can flip the spin, then it is an possible way to practice. And sometimes it is interesting to compare spin polarized and spin orbit couplings and results with them.